Hello, everybody. Welcome to today's Crime Seminar. Today we have two speakers, two talks. Our first speaker is Daniel Chen. He will be giving a talk on a principal framework for residual-based adaptivity in neural PDE solvers and operator learning. Daniel Chen is a third-year PhD candidate in the Division of Applied Mathematics at Brown University. He is broadly interested in applied probability with particular focus on stochastic analysis and interacting particle systems. Prior to graduate school, he was a software engineer, mathematical modeler at Northrop Grumman. He obtained his bachelor's in math and computer science from Case Western Reserve University, where he was the recipient of the Lajos F. Takacs Mathematics Prize and Computer and Data Science Research Award. With that short introduction, the floor is yours and you can start your presentation.
All right. Thank you so much for the introduction and thank you so much for the invitation. I'm very excited to be here and to share with you all work I did with my wonderful collaborators, Juan Vivek and Professor Darbon and Professor Kaniadakis, where we gave a principled framework to this general training method called residual-based adaptivity. I'll particularly view this in the context of PDE solvers and operator learning. Okay. And throughout, if there are questions, please just interrupt me, and I'm welcoming of any questions. Okay. So let's begin with a simple example, or kind of to get ourselves into the right mindset. I'll say I'll try to learn this function f, right? That's from some spatial domain I'll call omega to some real number. Okay, and for sake of simplicity, I'll just draw a constant function. That's the thing we're trying to learn. And maybe you'll come up with guesses for what the function is, right? So here's our first guess. Estimate 1 in teal here is something that's very close to the truth at most places, except for one. There's like a tiny region in space where I'm very off. Okay. On the other hand, maybe you can come up with if you use, let's say, like a different algorithm, maybe you'll come up with another estimate 2 here in purple. And well, how is it different? Well, maybe you're not so kind of on top of things anymore at most of the points, but you don't have this sharp peak, okay? So then you can ask, okay, which one is better, right? Which one, if I can choose between two algorithms, which one would I prefer? Of course, this is dependent on what your downstream task is later, but kind of just from like a purely abstract perspective, which one should you pick? Well, you can say, okay, let's measure the difference in L2. You can say, okay, I'll take the L2 difference of my estimate 1 and the truth. And by that, I just mean I'll take the difference between the dashed lines and the colored lines. I'll square it and I'll integrate over space, right? And maybe in this example, estimate 1 and estimate 2 have approximately the same L2 error. Right? But on the other hand, if I just change the metric, I say L infinity. So if I look at the maximum difference between my estimate and the truth, what happens here is that overwhelmingly, estimate 1, the maximum error would be all of this gap here, whereas for estimate 2, everything is bounded at most by this little gap. Okay, so very clearly, estimate 2 is better than estimate 1 in this metric. So how do we actually conclude that if estimate 1 is better or worse than estimate 2? So this is what we want to think about, and this is what will play a big role in what is to come. In particular, I just want to say, with this very kind of trivial example, that how you quantify the error really matters. Of course, this is probably trivial for everyone, but I'll just reiterate and get ourselves into the mindset that we're caring about how we measure errors. Okay. So let's move into kind of one step further. Let's contextify the problem, give the problem a little bit more context. I want to solve a PDE. That's the context we're in. So I have some differential operator in some function space, and we want a function u such that when I hit u with my differential operator f, I get 0 in the interior of some domain. And then maybe I'll enforce some boundary conditions u is equal to g on the boundary. Okay. But of course, solving this is difficult. So you want to say, okay, I actually have some class of functions I have access to. So I have a parameterized class of function, u theta, where theta here is the parameter, and theta would be parameter space throughout. And instead of saying that f of u is exactly 0, it's going to be some number that's not quite 0, because cannot get down to 0 exactly. Right, so I'll call it R for residual, right? And you have kind of interior, something on the interior and something quantifying the error on the boundary. And what is your goal? My goal is to minimize the total residual, say, right? So this would be like the interior residual plus the boundary residual, so that it's approximately 0, so that I'm approximately solving the PDE. Right? And I can write it like this. I'll say, I'll write my loss function L as a function of my parameter space theta. And it's going to be the integral of the residual of x squared, or the residual squared, evaluated at each point in space and integrated over space. Okay. So this is, I believe, more or less familiar to most people here. And again, we can look at the same picture, right? Instead of estimating a constant function now, we're just estimating 0. We're trying to get things down to 0. So on the y-axis now, it's not just some label space, it's now the residual. And I can try to minimize this proposed loss function, right? And it turns out that in practice, sometimes what happens is you will experience this little sharp peaks where at very little point regions of the space, you get very high residuals, okay? And to show that I'm not kidding, I have an example here. This is one of the examples we're going to later, but it's an operator learning example. But the point here is to say that, right, if you look at particularly this time point, the error here, there would have peaks all around, okay? So it's analogous to the constant plus peak situation I drew. Okay. So what people find that if we find these peaks undesirable, then why not just try to emphasize the peak so that we suppress it, right? So this is what people call like residual-based adaptivity, and it's proposed by many, many different authors. Many of the work is done by Chen himself. And it is just to say that instead of just considering the integral of R, I'll consider, say, the integral of R weighted by some factor lambda, okay? And then crucially, lambda can depend on R, hence the name residual-based adaptivity, right? So what I'm going to do is maybe when R is high like this, I'll put lambda also high so that my estimate focuses on the region of high residual. And maybe that gives me a more uniform residual, which is more desired. Okay. And empirically, it shows that this indeed is the case. I'll tell you what this label means in a second, but if you add some kind of reweighting in space to focus on the high residual parts, you do see the error tends to be more uniform. So the question we want to answer in this talk is to say, well, say given a goal, given I want to reach, say, error in what, or if my goal is to promote uniform error minimization, how do I design lambda? What are my trade-offs for designing lambda, right? And right, if I give you a lambda that works, do I know what actually it is doing behind the hood? Okay. So these are the questions we're trying to ask, and that I'll give an answer shortly. And we'll begin by doing a little bit of theory, and then towards the middle, we'll mix in some kind of implementation details, and at the end, I'll show you the numerics. But a spoiler, this choice of lambda here dictates the error metric. Okay. So I want to think that maybe if I choose lambda a certain way, I'm actually minimizing null2 loss. If I choose lambda a different way, I'll minimize null infinity loss, and so on and so forth. Okay. So let's begin with a first try at this. Okay. And the perspective we're going to take is by adding this lambda, we're adding some kind of regularization. So again, here's our problem. I dropped the squared because I can absorb the square inside the R. So without kind of sacrificing for notational simplicity, I'll just drop the squared. Right. Our goal here is to minimize the integral of the residual over space. And in practice, it turns out that if I minimize the residual weighted by some lambda, it works better. So we're trying to see how do we go from the left to the right. Okay. So let me rewrite it perhaps in a little funny way. I'll define this new measure, Q, right, as just like the weighted space. Okay, then you can see that these two now looks more or less the same, right? It's all the integral over R, but the underlying measure is different. Okay. Now you can say, okay, if I want to make it toughest on the person, right? If I want the most robust algorithm, what should I do? Maybe I should optimize over choices of Q, right? So if I try to do that inside the right-hand side here, I just take the supremum over Q over P here denotes the space of probability measures. So I'll assume that omega here normalizes to 1, but I'll pick over the space of probability measures of how should I reweight R. That is the optimal. And you'll see that it's actually equal to the L infinity. Right? And why is that? It's just that the optimum is achieved by saying, okay, I'll just pick with probability 1, I'll put all of the mass at the maximizer. So I can recover the L infinity norm easily. And in this case, it's bad. Right? Why is it bad? Because I can't really write it into this reweighting. So this is a bit too singular. It's like, if I know the answer, then I'll know the answer. So I don't want this. Right? Then what do? The classic trick is to add a little bit of a regularizer. Okay, so I'll introduce this metric called relative entropy, or more commonly known as KL divergence. And I'll write it in this abstract form, but for our case, if you want to take the entropy between Q and dx, it's just the log of the multiplier. Okay. So what this entropy does is this regularizes what I can choose for Q a little. So I'll try to avoid, or I'll stop the optimization from picking something very singular, like a delta. Now we can play the same game, right? I'll take a supremum over Q here to say, okay, what's the best way, or most robust way to minimize, to quantify my error? And then there's this theorem. So this is a well-known formula in statistical physics and probability called Gibbs variation principle. And the detail's not so important. It just says that for some nice enough R, this thing that we care about on the right before, if I take the maximum over Q, actually get this log of the integral of exponential form. Okay. So there's a clean way of representing this optimization problem in terms of something that's not optimization at all. And more importantly, actually know what the optimal distribution is. The optimal distribution Q star is exactly the exponential of R. Okay, normalized appropriately, so that's probability. So you should, I color coded here.
Daniel, can I ask you?
Yes.
Can you say something about the assumptions for the theorem? Just bounded and continuous R, that's it?
Yeah, bounded and continuous R, and omega has to be Polish, which is so complete separable metric space.
There's
Yeah,
nothing
so
on the H? No conditions on it?
Yeah, nothing on the H. I guess, yeah, H is the relative entropy here as we defined.
Yeah.
Other than that, it's no other assumption on the space.
Okay. Thank you.
Yeah, thank you for the question. Right, so I color-coded things here pretty intentionally in the sense that now this Q, right, if I want to achieve this supremum, I'll just pick my lambda to be this exponential weight. Okay, right here. It's the same colors here. Okay. So let's plug And we can look at this even closer. Right? This is actually it might be familiar to many people here. This is what they call the softmax function in computer science, or in probability theory, they're called the exponential tilt. And what it does is just says that, right, it's proportional to the exponential, and there's this free parameter epsilon here. So I can tweak the epsilon, right? If I have epsilon very, very big, this is in statistical physics called the high temperature regime, then everything kills the R, right? R over something very big is always going to be 0. And I normalize something that's very close, then it's going to be approximately uniform. So this is not so interesting. The interesting stuff happens in the low temperature regime where epsilon is very, very small. Now, what happens when it's small? So let's imagine if we're in discrete spaces, then the largest value is going to be exponentially bigger than the second largest value. Okay, so there's a huge gap between the first and everything else, the biggest value and everything else. And once I normalize it, it's going to peak at the maximum bar. So we can see this as kind of interpolation of the maximum function, hence the name softmax. And now let's plug this back into our data. Right? So here again, I have R. I want to understand what happens in minimizing lambda of R. I'll transform this to some regularized problem, and I'll take a maximum over Q. So I'll get on the left-hand side, but it gives variational principle, this epsilon log integral exponential term. Okay. But now you say, okay, this is a bit fishy here. Epsilon is just a free parameter. What should I do with it? So, okay, so let's pick the most robust epsilon as well. So let's maximize over epsilon. Okay. Now we can try to see what can we go do from here. So it turns out this thing is also very nice. If you squint a little bit at it and apply the logic that the biggest element is going to be exponentially larger than the second element, you can actually deduce some asymptotics in the epsilon equal to 0. In particular, this is known as Laplace's principle, or in the theory of large deviations, known as Varadhan's lemma. But surprisingly, the proof is difficult to find, so we provided the proof in our paper too. So it just says that for R that is sufficiently nice, if I take the supremum over epsilon of the quantity that I cared about from the last slide, this is equal to the essential supremum of R. And if this is continuous, it's just a maximum. Okay. And I'll give you a little proof idea because it's quite fast, kind of give you intuition for why this exponential scheme is going to be what I'm going to claim soon. So the proof proceeds via discretization. Right? Now just consider the case where I have two things. And let's say A is greater than B. And I'll consider the analog of this integral, which is just the sum. Right? So I have epsilon log e to the a over epsilon and plus e to the b over epsilon. I'll first factor out e to the a over epsilon, and I'll have this factor on the right-hand side. And notice that since a is bigger than b, b minus a is negative. Okay. So then I use log rules to pull out the a, and then I have this term on the right-hand side. Now, if I send epsilon to 0, what happens here? Well, first of all, there's an epsilon here, so it'll kill anything that's bounded. But also, e to the b minus a is negative. So b minus a over epsilon is very, very negative. And e to the something very negative is 0. So this thing converges to log of 1, which is 0. And the right-hand side completely vanishes. Okay. Right. And then to complete with to go from this simple case to the integral case, you just chop the space up and then do the same trick. But now going back to the diagram, what do we have? On the left-hand side here, I know by Laplace's principle, I'll get the maximum of R. And this is exactly the L infinity one. Okay. And to summarize, we have chosen a particular weight, right? The lambda that is exponential, so that when I do this kind of maximization on going to the left-hand side and down, I arrive at the L infinity. What about on the right-hand side? Right? If I just swap sup and the supremum here and the infimum here, I get like a dual formulation of the integral of r lambda, which is the thing we want, plus some regular, or minus some regularizer. Okay. I'll convince you in a second that we don't care about the regularizer. If we just cover this up for now, you'll see that we recovered exactly what we wanted for a particular weight. So here we're suggesting that to pick what weight, so if you want to minimize the L infinity norm, so if you end up here, you can push all the way back to arrive at the exponential. Okay. On the other hand, if you somehow come up with, okay, I'll weigh everything by softmax, what you're doing is actually minimizing the L infinity. Okay, so here's the algorithm. Here's a numerical scheme. What we'll do is iterate these 3 steps. Okay, I'll start by finding the optimal tilt. Right, I'll call this Q, and this is just the exponential weight. Right, and this has no computation step in it, just for the sanity of keeping track of quantities. And then I'll optimize my parameters with respect to this new measure, Q. Okay. And then I have this annealing step that I'll explain in a second. Right? So at every step, you're really just optimizing Q and you're picking a new epsilon. And this minimize step can take any first order or second order optimization scheme and doesn't depend on the parameters. Because the parameter is fixed. I already fixed Q. Right? There's nothing to do in the minimization scheme. And there's this free parameter that's the annealing scheme that as long as you send epsilon to 0, it's okay. So in particular, this is a choice that we make. So we have some constant times the maximum of R for some numerical stability over log K. And this over log K is inspired by simulated annealing. If you're familiar with simulated annealing, what you do is you slowly tune down the temperature so that you kind of arrive at the minimizer. Your ground state will be the minimizer. And there's a work of Stu Gieman that proved that this is the rate to achieve that. So hence we do kind of taking inspiration from simulated annealing because there's a very similar tuning down the epsilon step. We chose this schedule. I've hidden a very important thing in the previous step, right? I claim that this is an algorithm, but there's no way of computing this expectation. So I'll give you 2 ways of computing this expectation right now, and it corresponds to 2 different things existing in the literature that we point out as kind of corollary of what we're doing. Right, so one way you can do it is to say, okay, I specified this new distribution Q, so let me sample my collocation points according to Q, right? And then my estimate for the loss would just be 1 over n my loss of R of my collocation points, which are sampled from this new distribution. Okay, this is known in the literature as RAD. On the other hand, if you don't want to resample points every time, what you can do is say, okay, I'll have a fixed grid. It doesn't have to be uniform like this. It can be like randomly sampled. But what I'll do is I'll reweigh each sample point. Right? I have my lambda, which is just the exponential of the residual. Right? And at each point, I would say, okay, instead of computing just R of X, I'll compute R of X times my weight at that point. Okay? And this is exactly equivalent to this is the alternative formulation known in the literature as RBA. Okay? And really, right, they're the same thing by this change of measure argument that I've kind of embedded in my diagram. But both are equally valid. You can mix and match both. In the case of operator learning, which I'll get into, you can mix and match the 2. In general, you can just find the one that is either the easiest or gives you the best performance. Okay. I guess I'll stop here for a little bit for questions before I move on to the next part.
Then here you said that R was the R square, right? So this is essentially just the mean square there, right on the left. Like
Yes.
what
I
you showed.
observed the R in the R squared into the R.
Yeah.
Daniel, I also have a question. So you just looked at the L infinity and you show us also that you can do the L2, but can we do any interpolating? Can we do interpolating norms? Anything in between, like Paul Dupuy is doing interpolating norms?
Yes. Okay. Depending on what you mean by interpolating norms, maybe I'll talk about how to extend this very soon in the next section, and then you can tell me if I've answered your question.
Okay.
Okay. Okay. In that case, let's look at what's wrong with this exponential tilt, and then we'll move on to something that's more general. Okay. Right. So what we find in the exponential tilt is that, well, exponentials are strong. So if your loss looks like this, your optimizer kind of just exponentially focuses on the peak here. That's not necessarily good because you want some kind of smoothness. We're saying that we don't want something that's too smooth. We want something that's focused on regions of high residuals, but I can't just ignore everything. And in practice, you really need some kind of moving average to smooth out the exponential weight to get something that's numerically stable. Right? So the question that we asked ourselves is, then how can other weights be designed to get some desired uniformity smoothness trade-off, right? Uniformity in the sense that I want to suppress the high residual points, smoothness in the sense that I don't want to completely neglect like the lower, but not exactly zero residual points. Okay. And we'll do so by changing how we regularize the problem. Okay. So let's go back to the diagram again, right? Here, right, we started off with this problem. We want to understand what happens when we reweigh it. And I kind of just said I can add a regularizer. That's the entropy. Now I'm going to generalize this notion of divergence, statistical divergence, a little bit using what's called phi divergences. Okay, and I define it here. It's phi of the Radha-Nikodym derivative. Okay, and phi here is some convex superlinear function. So for example, I'll give you two examples. If I take phi to be x log x and minus x plus 1 is for cleanliness, then I exactly recover the relative entropy from before. Okay. And as before, dq dx is going to be lambda. So the phi divergence is just going to be the expectation of phi of my lambda, or of my multiplier. Okay. So now we've introduced a strictly greater class of regularizers. And then you can ask, okay, can we play the same game, right? Can we push back to the left and obtain something sensible? And then in this case, then we can try to analyze, asymptotics down here, and then we can analyze what the algorithm we get is down here. Okay. Unfortunately, the story is not so simple. Once you move out of the entropy regime, there's very clean, exact duality that you can get from log integrated exponentials in relative entropy. And that's part of the reason or part of the mechanism that drove all of the progress in, say, probability theory and many other fields. But if I abandon the structure, I don't have a clean representation formula anymore. In particular, I'll just take, right, again, R to be bounded and measurable. Then I don't have a clean left-hand side, right? Remember from before, I have the soup of integral of R plus the regularizer is going to be this log of integral of exponential. Now I don't have this. I just have this optimization problem that I have to solve. The upshot is it's one-dimensional, but it's still something that's not so explicit. Okay. And then recall the second part, we say, we actually know exactly what the optimizer here is. In this general case, we don't have it unless we satisfy some conditions, right? In particular, I satisfy a normalization condition. And if this is true, then the optimal Q is the derivative of phi. Okay, so phi prime is the derivative of the subgradient. Okay. So this is unfortunate, but let's try to go through what the keep the caveat on the side for now, and then we'll try to go back to our diagram and see what numerical scheme I can get out of it. Okay. Right, so here, I'll maximize Q on the inside here, and I'll arrive at this, what I call lambda epsilon. Epsilon is the free regularization parameter that we introduced, right? And this is not as clean as before. So when I take the soup of epsilon on both sides, I don't a priori know what this is, okay? So in fact, right, you have to do some work here. It's not clear what the limit is, but it likely is going to be something that simplifies everything. We'll show an example in a bit. But on the right-hand side, I have a perfectly fine algorithm. If I'm, again, ignore some of the caveats, right? I have the sampling of the same form, but my multiplier is now not exponential. It's the derivative of phi, my potential phi. Okay. So if we just do a little bit of sanity check, when you have exponential, this is the same thing, right? And so everything's okay. It's consistent. Okay. Yeah, so now let's get into, for a particular phi, what can we do? What can we say about the primal problem here? And what can we do about this lambda phi prime? What caveats do I have in my design choices so that I respect this constraint? So I'll consider phi to be r squared plus 1, which means that when I take the Fenchal dual, the convex conjugate, I get r squared minus 1, and it's known as the chi-square divergence. Okay. So it's a well-known divergence. And we can show that this limit of gamma, or lambda here, converges to the variance, all right? So variance here in the sense that this is just the L2, right? And then I minus the mean. So in some sense, you can see that it's if you choose phi to be this, you're solving an L2 problem. Okay. But if you're very sharp, you're going to see, okay, this problem is actually not well posed, right? Saying this is the primal problem is not a well posed problem because everything up to a shift, right? All constants have 0 variance. And if your residual is identically 100, that's no good, right? So we have to address some of the caveats of this. So recall that my optimal tilt will be constructed by differentiating my potential phi. In this case, it's just 2r. Right? So if I kind of close my eyes and assume the normalization condition holds, I want to retilt my distribution by this factor that's r, right? Something that's linear in r. Okay. And we come up with the exact same numerical scheme, right? I'll say my new distribution is now this r. I didn't normalize it because I assumed that normalization condition holds. Right? And then I'll minimize my residual according to this new measure, either by resampling or by reweighing my samples. And then I'll have some annealing scheme, right? I'll somehow send epsilon to 0. So, but now if you look at the normalization condition, what's a natural way to enforce this? Is to immediately enforce it here by how we choose the annealing scheme. In particular, if I just choose it to be the integral of r, then I can make this true. I can have the normalization have integral 1. Or I can normalize this properly. And everything will be okay. And if you recall from the theorem, this resolves the well-posedness issue too. I'm happy to elaborate on that, but in essence, if I choose the annealing scheme properly, so that the normalization condition is satisfied, I have a well-posed primal problem, and I have a proper algorithm that's within the framework. Okay. And in particular, this recovers the common choice of lambda, right? This r over the integral of r is a very common choice for how we tilt things. And now we know that it actually corresponds to an L2 primal problem, that's the L2 minimization.
Danny, so when we do the r squared here, when you say the common choice, this means that this is just the normal RBA, right? So if you do this trick, you get the normal RBA.
Yes.
Okay.
So we somehow found a way to explain what the normal RBA is doing by going through this diagram of
So
variation.
Daniel, this is where I have the question. So about interpolating norms or other norms. Let's say I want, let's say the L2 or like the so Bolev norm, or I want to weight alpha times L2 plus beta times H, so Bolev norm, right?
Okay.
I want to do that in my minimization. So is there any way to find the divergence function phi so that you will end up, and of course alpha and beta are weights to be determined, but that you can find an equivalent? Can you find from that, from targeting a certain interpolating norm, to going back and finding a proper phi?
Yes, certainly. Right. So basically saying that I have some norm that I want here, and I push back to find the corresponding lambda.
Yes.
Right. So on the top of my head, I believe all of LP should be fairly easy. So this is a one-dimensional optimization problem, and it's not so hard to guess what the solution should be in the case of LP. And then you can, so something like, instead of just r squared, I have r to the p, then it probably gives you an LP.
Danny, but when we had like this RP, you get something that was between P and Q, right? When you define your divergence as R to the P, then we get something that it's between RP and between LP and LQ.
Yes. So if asymptotically, your phi lies between some r to the p and r to the q, then you'll have your primal, I guess, problem would be somewhere in between LP and LQ. So I guess there are these asymptotics that you can try to play with. Like, I don't have a good way other than try to guess and check.
P can be one, L1, so you can recover then weights for the L1.
Yes. Oh, L1 might be difficult just because
that's what I'm saying.
Not,
P for P greater than 1.
P strictly greater than 1. Because we need the superlinearity.
Yeah, exactly.
Yeah. And for Sobolev norms, I'm not so sure. I have to think about a legitimate norm to see where would kind of the derivatives come in. But perhaps if we lifted the formulation up to, say, more coordinates, I probably can accommodate for Sobolev norms too.
That would be a good extension, especially for GANs, for example. I know papers by Dupuy and Marcos Katsoulakis from UMass Amherst, where they have they work a lot on gamma divergence, interpolating norms, and lots of different things that show that training could be easier.
Yes.
Yeah.
Right, exactly. And yeah, it certainly, yes, this generalized Gibbs variational principle, I think, was taken from one of their papers in this direction too. So it'd be interesting to see, right, if I extend this class of a regularization even more, what kind of algorithms can I come up with in the context of PDE solvers? Okay. So in summary, I'll just tell you about, now we're officially done with most of the theory part. I'll just tell you in summary what we have done. So what we're proposing is a kind of a unified framework for understanding this residual-based adaptivity. Okay, and just some practical benefits include, like, it's easy to implement, and it's easy to design in the sense that you can pick anything you can dream of for lambda, and we see that, you know, having lambda depend on R can correspond to choices that are optimal. Right? They're principal ways of deriving these choices. We'll show in a second that it consistently outperforms across various benchmarks, and it's compatible with, say, operator learning, which I'll not go into detail here. But right, recall that Professor Karniandakis had a great question saying what assumptions are you putting on the theorem? And we're putting very general assumptions. We just say omega is some separable metric space, which means that most of the function space theorems can also be applied here. So we can apply this to operator learning, and by mismatching, resampling and reweighing in both like how we pick the function space and how we pick the spatial collocation points, you can get very good results. It's also compatible with higher order solvers, right? The minimization step doesn't say how do you minimize, it just says to minimize it. And it turns out that we combine higher order solvers by these reweighing schemes, we get very good performance as well. And I guess the main selling point here is that you can dream of any weights you want, and then you can do some math to get what actually you're doing. Right? So for us, if I say I dream up the exponential weight, then I'll do this Gibbs variational principle and Laplace principle to get that I'm recovering an L infinity problem. If you do a little bit more work, you can say, okay, the linear weights correspond to an L2 problem. And I know how to do this for a wide class of functions phi. Of course, you can do it the other way around. It may be a little bit more work, but certainly doable. If I have a target primal problem, what should my weight be so that I do it kind of this regularized and uniform way? Okay. Now I'll show you just a series of results. So first we can compare our methods with some other existing methods. And you see that we don't really require a lot of, we use the things that we say that we're using, plus kind of Fourier feature embedding, whereas many other people have to use something more complicated. And we're not really picky about the optimizer as well, but we get really good optimization outcomes from second order solvers. Yes.
Maybe one thing, if I can comment here, is like if you see that the second best performing, which is Jorge's paper and Ilham's paper, they use RAD, which is, as Danny explained a few slides ago, is a version of BRBA. So essentially they get that good performance with a version of BRBA because it's like we're just somehow formalizing the trick that people generally use.
Yes, yes, exactly. Yeah, one of the main contribution here is that we generalize. We can generalize and identify what people are doing previously. Okay. And there are kind of four main selling points. The first selling point is that it accelerates convergence. Right? We ran this across several kind of canonical test cases like Allen-Kahn and Burger's equations, as well as for operator learning, right? For bubble growth dynamics and Navier-Stokes or wave equation. And you can consistently see that regardless of whether you use the quadratic weighting or the exponential weighting, you decrease towards the minimum very quickly compared to not doing these adaptive weights. Okay. And of course, you can also quantify in terms of other metrics, right? We promise that we'll achieve a better L2 error or I guess in this case, we'll use exponential weights. We promise that we'll achieve a better L infinity error, right? Because that's the primal problem we're solving. And you can see that this is consistently the case. In fact, for both L2 and L infinity, which is quite surprising. So, okay. The second thing is kind of go hand in hand with the previous one, but more in the flavor of what I was trying to motivate in the beginning, that by modifying my primal problem, I can really kind of get a stronger, I can dictate my mode of convergence a bit more. Well, I didn't label this, but I believe this is for Burger's equation, right? And you can see that there are high peaks in the residual for if you don't use anything, but you have very consistently low, not as peaky residual landscapes if you use VRBA. And this kind of captures the fine details a bit more. This is for operator learning, for the bubble growth dynamics. And you can see that if you don't use these reweighing, you lose these fine details here. Whereas if you kind of reweigh it a little bit, this is for the exponential weights, you can capture all of these details. Okay. again, this is for, I think, the Navier-Stokes equation. It's the same picture, right? These have their high peaks. This is, in fact, the first picture showed. And if you reweigh it, the high peaks go away. And then the third point is actually it reduces the variance of my loss estimate. This is what inspired the work in the beginning. In the beginning, we thought that what we're doing is actually some important sampling scheme, which we, in some sense, are, but not exactly. So the difference between VRBA and important sampling is in important sampling, you have a fixed problem, right? I want to compute the integral of R. I'll do it by tilting it to a different measure. But here we're completely changing the problem. We're not trying to solve the original problem. We came up with a new problem, right? I want to minimize the changed weight or the integral of some weighted loss. And to accommodate that, we have to do all of the additional theory to explain what it is doing. But nonetheless, it has the important sampling flavor to it. If you look at the variance of the estimates, you see that it's very consistently much lower than if we don't do any weighting. And okay. And lastly, we find that it accelerates learning. Now, I'll explain what this means. So in learning theory, people commonly observe that there are 3 phases of learning. Okay, so what you do is you partition the space, right, your domain, randomly into different chunks. They don't have to be like distinct spatial chunks. It can be just random points. And I'll align at every gradient step, how well does the gradient align to each other across the partitions, okay? And I can somehow quantify the alignment by this thing called signal to noise ratio, which is the SNR over here, okay? And pretty robustly, people observe that there are 3 distinct phases. So first, the SNR would be high, so everyone would be aligned, but I'll have high error because it's just at the start of the training. Everyone agree for a while, and then people start getting confused. By people, I mean the different partitions. And when there are conflicting gradients, they kind of cancel out and you don't move as much until eventually you find the right direction and everyone agrees again. And that's what we call the diffusion phase, where learning is the most productive, okay? So what we're seeing here is that when we reweigh it, we consistently go into the diffusion phase much faster. That's like the diffusion phases are over here. And I have consistently a higher signal to noise ratio quantified. You can see the gaps here between the red and the green and yellow. Right? So this is kind of a posteriori justification for why reweighing is doing so well. It's kind of, I'm giving each of the gradients a sense of direction, or a more stronger sense of direction to tell them where to go, and kind of, which in turn leads to better generalization. Okay. So we can see this in both like the pin examples and for operator learning examples. So again, the top is generalization error, so the lower the better, and the signal to noise ratio is higher the better, and we go into this diffusion phase a bit quicker. And I guess with that, I'll thank you all for your attention, and I'll take any additional questions.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker? Yes, Socrates.
Hello, hi Nazanin. How are you?
Hi.
Hi Daniel, it's Socrates from EPFL here. Thank you for the nice presentation.
Well, thank you for joining us.
This principle seems like a nice approach to express the different residual-based schemes. I just have 2 quick questions to understand a bit more how this framework works on the dynamic sense.
Okay.
So, from what I'm understanding, in the derivation, you do some, for the variational objective, you start from the max residual formulation and you soften it into a dual form for a fixed function of residuals R. So I think it was in the Gibbs expression you showed in slide 4 or 5, I think.
Okay, let me go. Okay, so point to me, is there an arrow that is...
If you go to slide 4, where you showed the Gibbs equation.
Okay. Yes.
So here you have, you define the equation with respect to x, but there's no theta which dynamically changes the shape of your residuals here. So
Yes.
you kind of have a static function of residuals, and that's how you end up in the dual form, if I'm not mistaken.
Yes, so here I kind of, it's a notational choice. I just suppressed dependency. So for like cleanliness of the presentation. But here you can certainly add, or I guess for each, yeah, we're doing it for each theta, you have this representation.
But does it apply on a dynamic sense, the Gibbs equation and Laplace equation, I think?
Yes, yes, yes. So
Okay, and so how does it translate to the dynamic case where theta are updated during training and the
okay,
function
I
of
see
R
what
is constantly changing?
Yes, I think I see what you're saying. So right, as written here, it doesn't seem like right, theta is evolving in time. I'm not respecting the dynamics, right? So, but we're actually doing it here. We're thinking of it as in for every fixed theta, I can get this new Q, right? Which then I'll minimize according to this new measure.
Okay.
Right.
So it
And
holds
then
for any fixed theta,
yes,
basically.
yes. I'm not, yes, yes.
Okay,
And then
but
yeah, go ahead.
yeah, so basically during the update of theta, you have a dynamic scenario where you still need to stabilize the whole situation with some kind of heuristic annealing or exponential averaging, like we do in Adam, for example. Because in the VRBA, you use like the exponential average and annealing techniques.
Okay, I'm a little bit lost as to which part are you referring to?
So basically, I'm trying to understand how the static theta translates to the dynamic scenario where the thetas are updating.
Okay.
Does the variational principle hold in that case, or you still need some kind of heuristic stabilization techniques like the averaging, the exponential moving averaging of residuals?
Yes, yes. Okay, I see. So yes, for each fixed theta, I have the duality. I'm not sure what would it mean if I don't know if there's a way to incorporate the updating of theta inside the variational principle. And in practice, we do say let's keep a history of the weights, and I do some exponential moving average on the weights themselves to smooth the problem out a little bit, particularly for the exponential weight.
Okay, so the principle does not directly address the stabilization techniques which are required to help
Yes, it does not.
us
Yes, it does not
stabilize the
address
dynamic case, basically, which remain heuristic. It's
Yes,
not
those
even in
remain.
Adam, like you cannot for non-convex objectives, there are no guarantees for the
Yes,
exponential moving average.
yes, those remain heuristic. Yes.
Okay, okay. Yeah, I think I merged the two questions in one, basically. So
Yeah.
I'm okay. Thank you very much.
Okay, great. Thank you.
Thank you.
Thank you. Do we have any other questions for the speaker? Any comments?
Daniel,
Okay.
for the people who do important sampling, right? So they
Mhm.
do the sampling. They don't do weights, but they do the, let's say, important sampling. Can we go back and find what weights this corresponds to? Because you have this correspondence between the Q, the distribution, and the weights, right?
Yes.
So did you guys look at, you and Juan, look at what weights will come out if somebody who is doing important sampling, what kind of weights are actually using?
I believe we can do it. So Juan, feel free to jump in. I believe the canonical choice is in the literature is this linear weight, which we can go back to say that they correspond to some primal 2 problem.
Yes, that's exactly right. For example, with this special type of potential, you recover both RAD, which was introduced, I think, in Lulu's and Chengshi's paper, the exact formulation from them, and the exact formulation for the RBA that we were using. So this quadratic potential works for both cases. What people wrote
So
this time.
So then where does the important sampling come in? It comes in the particular Q that is used, the distribution.
Yes. Yeah, exactly. So in RBA, we use the Q, we transform the Q on our lambdas, and in their case, they transform their Q into the distribution that they are using to sample. But it's essentially the same one. The rule that how they are computing their probability.
So at the end, if we do this exercise, at the end, what weights corresponds to important sampling?
Yeah, RBA and RAD are the same.
Still RBA.
RBA are the same. RBA and RAD are exactly the same weights. So the equivalent weights of RAD is RBA. Yeah.
And if I do another distribution?
Then I would.
Yeah, then you can do the. Well, if you do something else, then we can always. There's always a change in measures, which would always give you the weight, and we can do the same thing backwards and try to deduce what the final problem is.
But it would be technically directly because the lambdas are just like a non-normalized distribution. So if in their paper, let's say that people X is doing some method B and they put what is the weight that they're computing their probability, you just get the RBA just by non-normalizing the weights to give them some properties. So just multiplying instead of sampling. So yeah.
Sorry, I just thought of another quick question. So I think I saw in some slide there was 2 columns where you showed the optimal weights for each norm. And I remembered I wanted to ask, in what sense are these weights optimal? Or are there any guarantees for their convergence properties in order to be called optimal?
Yes, optimal in the sense that I'm maximizing over Q in this era.
Okay. But it's not in a sense that you get like the optimal convergence rate, for example.
No, that's very largely
okay.
There would be like the weights that satisfy. I think that they're the exact solution of this dual problem, for example, for the case radial infinity. Yeah.
Okay.
But also, yeah. Also, if I may comment one more thing about that is like this also gives it like quite open because, for example, this also somehow justifies like a self-adaptive weights because ideally you could also take this Q not as a function of the residuals but as learnable parameters, and then that's how. And if you think about it, it's exactly what the self-adaptive weights were doing. They're just using a gradient ascent for the Qs. So then you get it back from here too.
Yeah, no, I think most of these weighting techniques are trying to do similar things, but yeah, it's nice to see that they can be linked in a way. Okay, thanks for the clarification.
Thank you. Do we have any other questions, comments? Because I think it's time to move. It's time to move on to our second talk. Thank you so much, Daniel. Our second speaker is Jiaosheng Yi. He will be giving a talk on cooperative variance estimation and Bayesian neural network, disentangle, aleatoric, and epistemic uncertainties. Yi is a PhD candidate in mechanical engineering at Delft University of Technology, supervised by Professor Miguel Besa. His research focuses on Bayesian neural networks, uncertainty quantification, multi-fidelity modeling, with application to data-driven constitutive modeling and material design. His broader goal is to build reliable and uncertainty-aware machine learning methods for scientific and engineering applications. With that short introduction, the floor is yours and you can start your presentation.
Okay, thanks for the kind introduction. Hello, everyone. My name is Jiaxia, and you can also call me Yaga. And I'm a PhD student from Delft University of Technology, supervised by Professor Miguel Besa. And today it's really my honor to give a presentation at Crunch Seminar. And my topic will be about cooperative variance estimation and Bayesian neural networks that disentangles aleatoric and epistemic uncertainties. And today, my presentation has the following 5 aspects. First of all, I want to bring your attention to the plastic recycling problems. Nowadays, we are using more and more plastics, and that has created serious environmental issues. However, for all the used plastics, most of them, we just use them and store them away, and only a small portion has been properly recycled. And there are 2 technical routines that can help us to recycle plastics. The first one is chemical recycling, and the second is mechanical recycling. And as a PhD from a computational group, I mainly focus on mechanical recycling. And among the widely used plastics, polyethylene and polypropylene are the 2 most commonly used polymers in the world. So our expectation is that we have these recycled plastics, and then we send them to the factory, and ideally we can get this 100% pure recycled plastics. However, if we take one of them and then take a micrograph, we will find out that the reality is that these recycled plastics, for instance, in this case, this high-density polyethylene is impure. It always contaminated with, for example, low-density polyethylene or some sand. So this impure mixture of plastics with those unknown relation because of the recycling process give us some difficulties when we want to create better recycled plastics. The first thing is that imagine this is the virgin material, but because of the recycling process, its mechanical property becomes uncertain. And the second thing is that during the recycling process, it's really difficult for us to separate PP and PE. So that motivates us to form them as a composite. But the annoying thing is that even in this case, we found another issue. That is, PP and PE, they do not mix well. As we can see here, if we put them together, it simply gives us low mechanical properties. And the problem for us is that how should we do to improve the mechanical performance of those recycled sustainable material? And we got some tensile tests from our industry partner for this PP and PE mixture, and we found out they are quite brittle. It breaks very soon. And one approach from the literature is to add compatibilizer. So meaning between the PP and PE interface, we can add a layer of glue. And with compatibilization, we found out its mechanical property improves. And the things that with different compatibilizer, we end up with different composites. And we can see that their material properties varies a lot, but associated with different level of noise, of variation in the failure strength. So if we want to design such recycled PP and PE composites, the goal for us is to consider two things. For example, we want a material has larger failure strength, but also at the same time, it can give us smaller variation in the failure strength. And of course, in the lab, we can use trial and error. We can change different compatibilizers, and then we try to explore which compatibilizer leads us better recycled material. However, this trial and error process is very time-consuming and also very costly. And in this case, we want to use machine learning techniques because, as we know nowadays, in the era of artificial intelligence, machine learning models can help us really to accelerate the process of design and analysis of materials and structures. And so remember, if we have this data set, we can simply try to put them into a machine learning model, and with all of this statistical information, the machine learning model could potentially easily tells us maybe the material with the pink is better. However, practically, when we are collecting the data for each material, we may only collect one sample. And if I give you this data set, can your machine learning model do a right choice, give us a better material? I think probably it will not. So we know that we want to use data-driven models, but the most importantly, we need data-driven models with uncertainty quantification. And in that case, it motivates us to propose our new method. But before going to the details of our new method, I want to give some clarification about some terminologies. The first of all is, what do we mean by uncertainty quantification in the context of data-driven modeling? So imagine we have a 1D noisy problem, and it's a 1D toy problem. We can just simply sample between 0 and 10, and it can give us this noise output. And with data-driven models, what we simply can do is that then we can train several models. For example, we train model 1 and model 2 and model 3. By ensembling them, then these models can give similar predictions in the region where we sampled. But in the region where we don't sample, their predictions varies a lot. And this variation comes the machine learning models, we call it model uncertainty or epistemic uncertainty. Usually, this is because a lack of knowledge. So we can potentially reduce this model uncertainty by adding new samples, for example. And then another thing is that, what do we mean by noise? So here, go back to our toy problem. If I give you the code I'm using to generate this toy problem, we will find out it actually has a really smooth ground truth mean, as we can see here, of the dashed blue curve. And because of the noise, the samples that we get is deviated from the ground truth, and but surrounded it. So noise in the context of data-driven modeling, we usually call it data uncertainty or aleatoric uncertainty. And usually it is irreducible. And if the noise or aleatoric uncertainty is input dependent, for example, as we show in this case, the bandwidth is different at different input variables, then we call it heteroscedastic aleatoric uncertainty. But if the noise is the same everywhere across the whole design space, then we call it input independent or homoscedastic. So then by the method, if we want to do a literature review that about the data-driven method can give us uncertainty quantification, we may end up with Bayesian machine learning or simply Bayesian neural networks. Usually, it assumes that our observation y equals to our ground truth function f of x plus a noise term. And we usually assume the noise follows a Gaussian distribution with zero mean and a variance of sigma square. And conceptually, Bayesian neural network has the same architecture with deep neural network. But the only distinction is that instead of putting the weights into real numbers, Bayesian neural network set the weights into random variables, meaning give the weights have a distribution. And instead of doing optimization to get our neural parameters, we have to use inference. So with for the base rule, in this setup, we have several important recipes. First of all, we need to have our prior for our neural parameters, which could be a distribution. And then we have to define our likelihood. In this case, the likelihood is just a forward propagation of our neural network. But importantly, we have to make sure the data noise is being properly encoded in this setup. So with our prior and likelihood with the base rule, and we can get our posterior distribution. And so in theory, with Bayesian neural networks, we can have our mean prediction, aleatoric and epistemic uncertainty prediction in one go. However, in this case, it is very difficult to train everything at once. And here, I'm giving you the prediction of using Bayesian neural networks in one go for our toy problem. And here we can see the prediction are compromised. So that triggers me to think why training Bayesian neural networks in one go is such difficult. In this case, it took me actually a while to figure out why. So first of all, I want to use the following several slides to explain. First of all, if we have our posterior, if we have our prior and likelihood being Gaussian distribution, and then we can easily write our prior formula like this by taking the logarithm. And first of all, if we only consider this right part, we easily can find out this actually is our MSE loss plus the width decay. And if we only train it deterministically, and then it goes back to our DNNs that we use every day. So we have our input, hidden layer, and output, and the weights are being numbers. And using optimization to minimize this loss, we can easily get to a local optimum gives us predictions, or a global optimum gives us better predictions. We use this part every day, and but we know it is difficult to tune the hyperparameters. But by doing so, we only get one quantity, which is the mean responses. There's no uncertainty information out of this model. And then we may try to do a bit more. So in this time, we may think about why not optimize for the posterior. In this case, we're just trying to set up a deterministic chaining with the neural network and then optimize for the prior, in this case, the negative log prior. And then by doing so, it will give us the mean and aleatoric uncertainty prediction. But again, the training could be very difficult, and I will explain to you why later. And this procedure actually could optimize the negative log likelihood or a point estimate. And by doing this, it also doesn't give us the epistemic uncertainty estimation. And what happens for Bayesian neural network is that instead of minimizing for the posterior to get a point estimate, Bayesian neural networks, for example, sampling method, it tries to integrate the posterior distribution. So to get the area of this loss landscape, in this case, it allows us to estimate the epistemic uncertainty. But of course, we have to pay the price. It will be very computationally expensive. And as I mentioned before, it's unstable and difficult to separate both uncertainties. So for now, that triggers me to think, can we have a method that can simultaneously predict us the mean, aleatoric uncertainty, and epistemic uncertainties? So in this case, I propose this cooperative variance estimation Bayesian neural networks. Actually, this is also very easy. Imagine we have our problem on the top left. This is our ground truth with the samples being located between 0 and 10. And our VBNN actually consists of 3 steps. In the first step, I propose only to train a mean neural network deterministically. In this case, we can just follow our daily routine, trying to minimize for the MSE loss. And then in this case, after the step 1, we can get to our ground truth mean prediction. And then by doing so, we go to our second step by fixing the mean prediction. In this case, we train another neural network called variance estimation neural network, only trying to capture the aleatoric uncertainty. That gives us the noise estimation, as we can see here in the orange part. And with this information, then we send our chaining to Bayesian neural network chaining, and by fixing the aleatoric uncertainty, and then just doing Bayesian inference for the mean, and it can give us an updated mean prediction and also the epistemic uncertainty for the mean. So with this VEBNN, we are trying to solve things sequentially but easily. And you may ask, hey Yaga, why we need to separate where? So first of all, is that when we have to separate step 1, step 2, the thing is that when we look back at the log posterior again, and then if we want to minimize for this simultaneously, we found it is very difficult to take gradient for this Gaussian posterior, because, and here I'm showing you the gradient with respect to the mu and sigma square, and then we find out there's a high order term in the denominator, and that leads us to a suboptimal. And as I'm showing you here, in this case, it starts to give overconfidence variance estimation, and then that compromises our mean prediction. But here I'm giving you a comparison of separate chaining on the right. So the left still is the joint chaining, as we can see the results previously. And on the right, we first train a neural network for the mean only, and then based on this mean, we train a variance estimation neural network. And as we can see here, this overconfident variance estimation issue has been solved. But here has a one tip. So in the second step, instead of just fixing the mean of our Gaussian posterior, we try to minimize a gamma likelihood loss here. And why we choose a gamma loss for the second step? And the reason is very simple. So imagine at the first step, we already get a good mean estimation. And then since we assume our noise follows a Gaussian distribution, then we can easily demonstrate that it's squared residual follow a gamma distribution. In this case, in the second step, we have a small neural network that trying to minimize this gamma loss. And then this expression gives us the estimation of our original aleatoric uncertainty estimation. The good news for this gamma loss is that taking gradient for it is very easy. There is no high order term appears in the gradient, so it can stabilize our optimization procedure. So for now, we have our first step and second step, and then we look back to the posterior that we want to integrate for the step 3. We will find out two things which are really good for us. The first thing is that we already get a warm-studied mean. And the second thing is that we already get our estimation for aleatoric uncertainty. As here we can see, the blue part can be fixed. So with this information, then if we do Bayesian inference based on those information, it will be much easier. It will become much easier and no numeric issues later on. So in the third step, actually, then you can just pick your favorite inference method. For example, you can go for a Markov-Chain Monte Carlo if you want, or go to variational inference or some others like ensemble and so on and so forth. But of course, we cannot claim the advantage without doing any experimental validation. In this case, we first want to show the one-dimensional case. In this case, we tried 4 different inference methods like ensemble, MC dropout, and there's a variational inference method called BBB based by back propagation and PSGLD. And we found out actually the bottom line is our method. We found out cooperative chaining always performs better compared with joint chaining with the same inference method. And in this case, in this problem, PSGLD performs the best. And then we further try to
Did you try?
test its
Sorry, I have a
performance.
question. Did you try HMC?
Mhm.
Did you try HMC?
Actually, we tried, but not in this presentation. We tried
Because
in-house.
HMC is sort of the golden standard. So
Yes, but it's also a bit more time-consuming compared with this
it's expensive,
inference
yeah.
method.
But for accuracy, is the I don't think you can beat the accuracy.
Yes. Actually, it gives us the same performance.
Thank you.
Okay. Then we continue to explore its performance with different churning points. Here, we changed the churning points from 20 to 400 for this problem, and we also found out our churning scheme actually performs better. And then later, we started to test the performance on public problems. And one bottleneck is that in the public problems, we cannot find a data set that gives us the true aleatoric uncertainty, which makes it difficult to say whether to test whether the uncertainty disentanglement aspect is good or not. But still, in this case, we try to compare according to the test log likelihood matrix. In this case, also for inference method, and we reported the TLL for the UCI regression data set. And here we find out actually, again, PSG performs the best according to this full inference method. But here I want to draw you the attention to one inference method called BBB, because if we take BBB and jointly try it, we find out it almost diverges. However, if we take VB and N on this case, it turns the divergence to comparable performance, which is very encouraging. And then later, in order to test the performance of uncertainty disentanglement, which is our main goal, then we created a dataset called plasticity law discovery datasets. In essence, this dataset, we aim to learn the history-dependent plasticity law of a 2D material.
Yeah, could you go back to the previous slide, please?
Yes.
George, so here I think the logic is exactly the opposite of what you said. So BBB is a very, I would say, weak inference method. And the point that he's making here is that even using a very weak Bayesian inference method, and so the solution is actually quite poor when you train everything at once to get all three metrics, right? Mean, aleatoric estimation, and epistemic estimate as well. It doesn't work, right? But by separating it, it almost gets very similar performance to the stronger inference strategies that you have. And of course, HMC is the best and the most expensive. So for the bigger data sets, it was quite challenging to actually do it as well. Does that make sense, George?
Yeah, sure. Thank you.
Okay. Yes, thanks, Miguel, for this. So for this plasticity law discovery dataset, again, we want to explore another important property, which is the uncertainty disentanglement. And in this case, we were trying to apply this history-dependent strand path to the 2D material at the three tension at the three directions simultaneously, which are the two tension directions and the shear direction. And after simulating, we are trying to collect the corresponding homogeneous stress curve for these three components. And our ground truth here is the RVE. And as we can see, the responses is in the black curve here. But because we don't have enough computational resources to get RV simulations every time. In this case, we have to use SVE, which are smaller pieces of a material. And in this case, that gives us stochasticity. And as we can see here, by different realizations of SVE, we will end up with different stress curves here. And this problem is multidimensional and with history-dependent sequence pairs. And the aleatoric noise originated from the material, and it is heteroscedastic in both in different inputs and also for the same inputs at different loading step, as we can see here.
Perhaps you can define what I don't think this audience knows what RVE is. Maybe you can say a sentence about that.
Yeah. So in computational material science, RVE is called representative volume element. So it's the most it's a representative of a material that we can use to simulate the material properties. So you can imagine RVE just is a kind of a material, and it has the most it has all the statistical information, and it almost gives us the same responses when we repeat it when we repeat the simulation. Yeah. So in contrast, SV is the smaller pieces, as we can see here, and that will give us stochastic information, as we can see here. So in this data set, that gives us the ability to get the ground truth distribution. But one thing we have to notice here is that the ground truth distribution is not only for the testing purpose. So for the Chen data set, it will be still noisy, and no single input sequence will be simulated twice, meaning there's no information leakage from training to testing. And in this case, we send this data set to the VBNN, but in this case, we have to use RN architecture because it's a time-dependent problem. And in this case, in order to thoroughly evaluate the proposed method, we have to use multiple accuracy metrics. And I will get you through one by one. And first of all, is the quality of the mean estimation. In this case, we have different methods. And again, our VBNN performs really well and is almost comparable with the ME, which is the mean estimation. And then if we go to check the quality of the aleatoric uncertainty estimation, we will find out, first of all, the mean estimation neural network doesn't have this ability. And second, our VBNN performs almost the best, even though we find the MVE point estimation is very close, but in the data scarce scenario, we also outperform with them. And then we go to check the quality of the epistemic uncertainty estimation. In this case, we have to use three metrics, although the logic is that we want a method to achieve a target test coverage here in the middle with a smallest test interval length. And then that can lead us to a higher epistemic test log likelihood. So in essence, we want our predicted epistemic uncertainty distribution to be narrow enough to cover a given ground truth samples. So in this case, those mean estimation neural networks, they don't have this ability because they don't provide epistemic uncertainty, as I mentioned previously. And among the method that can give us predicted epistemic uncertainty, we find our method, which the red line here also gives us the best because it uses a tighter distribution, but gives us the highest, the closest test coverage to our target. So overall, with this VBNA, we achieve an important ability, which is give us the capacity of disentangle these uncertainties. And also, I'm now showing you the uncertainty identification for a given path. So here is the prediction with only 100 training passes. We found out the left is the aleatoric uncertainty, and right is the epistemic uncertainty. And then when we're increasing the training passes, we are finding these predictions at left is more close to ground truth here. And we also find epistemic uncertainty is shrinking. And then with even more training passes, we find out this actually really overlap to ground truth, as we can see here, and end up with a epistemic uncertainty, which is very tight, but still it hugs our ground truth mean here. So for now, we have this method, and we also already showed that it is capable of predicting us the three important quantities: mean, aleatoric, and epistemic uncertainties. And what can we do with this method? So I hope you still remember the problem of sustainable material design in this data set. So in order to deal with this problem, first of all, we developed a finite element method. This method can help us to simulate this recycled PP and PE model system. And with this simulation, we can get the material properties, for example, the failure point and associated toughness. And by choosing three input descriptors here, those are the weight fraction of our PP and weight fraction of our compatibilizer and associated material properties, which is the Young's modulus here, EC. And here we care about two quantities, the failure strain here and associated toughness. And we found out this is a really noisy problem. And here I'm showing you several test points by fixing the weight fraction of PP and PE by only change the compatibilizer material properties. We found out it's nonlinear and also has really large data noise, as you can see here. And by sending this data set to this VBNA, first of all, we can get fast prediction with our quantities. Here, I'm showing you the predicted three test points for the predicted toughness. And from the left to right, I'm fixing the weight fraction of compatibilizer and the Young's modulus of the compatibilizer by only changing the weight fraction of our PP. And we see here the histogram is the ground truth simulated by a finite element method. And the orange prediction is our aleatoric uncertainty estimation. Actually, it fits our ground truth very well. And also, our predicted epistemic uncertainty here is very tight, but again, it covers our ground truth mean. So in this case, with VBNA, it really gives us the capacity to predict our recycled sustainable material. And having this, then we are thinking about the design problem. So how about design better sustainable materials? In this case, we select trying to optimize for the toughness, but also trying to reduce corresponding aleatoric uncertainty. And here, based on the Chen VBNA, we carried out multi-objective optimization, and the heat map gives us all the evaluated points. And with this, we can really see, we can really tailor our material properties. For example, if I only want to have a polymer which has a predicted aleatoric uncertainty of that toughness about 0.2, and then we know where to go. And the most interesting thing is that the Pareto front here gives us all the optimums. And then by looking at the Pareto front, then we can make different choices. For example, we can say, okay, I don't care about our my noise. I only want to maximize for our mean responses. And then here gives us the blue design here. Or you can say, I don't want to care about the mean prediction. I only want to have a minimal aleatoric uncertainty, and that gives us the orange. Or you can think about a combination like maximizing for the mean, but also considering a 95% of the confidence interval, and that gives us the red design. And then by sending back those designs back to finite element method for validation, and then we actually get the ground truth. And we here also I'm showing you the predicted aleatoric uncertainty. And all these three design schemes remain predictable. But the good news is that we now can find out different materials with our purpose. So for now, with this VEBNN, we can really design a sustainable material with expected mean performance, but we can really tailor its data uncertainty, make our design more well under control. So with this, I want to conclude today's presentation. So overall, I propose this new method called variance estimation based on neural networks. It is scalable, robust, and can be generalized to different model architectures. And it achieves a really difficult task, which is uncertainty disentanglement. And I successfully applied this method to history-dependent material law problems and to design sustainable materials. And for the future, I think we can consider to extend this to multi-fidelity or do uncertainty quantification at scale or do Bayesian optimization and active learning. I think that's all my presentation. Thanks.
Thank you so much. Do we have any questions for the speaker?
Hi, Joshua. Hi, Joshua. Nice talk. Yeah, I'm a PhD student here, and I have questions about the cases you consider, because I think I saw that you all consider the cases where you have the data during the domain and you don't have the data between these two endpoints. So how about the gap data if you only have the points at the endpoints and you don't have the data in the middle part? So if you train the mean function, if you first minimize the MSE error using the MSE loss, but in this case, you don't have the observations at the midpoint. So maybe in this case, the mean prediction will overfit. So in this case, can your framework still achieve good performance?
Thanks for the question. Actually, it's a very good question. Yeah, so in this case, actually, that's the reason why we have these three steps. So in the first step, we only care about the mean, but remember, we have our third step. That is the Bayesian inference part. So in that case, it could update our mean so that it can adjust such that in the case where we have data, then it gives us lower predicted uncertainty. But then in the middle, as you mentioned, if there's no data, then at the final step, Bayesian inference method will increase its predicted uncertainty. That us know in that region, it is less confident. So actually, there's no problem with our proposed method.
Okay, thank you. Yeah, because if you minimize the MSE error in the beginning and you got a mean prediction, but in this case, if the mean prediction is much different from the ground truth, so when you in this case if you still use HMC or some other sampling methods to train the mean function, well, what's the difference between if you initially just use HMC to get the prediction? So in the middle part, maybe you cannot get very good predictions even you train the HMC, or you can just initial use the HMC.
Yeah. So actually, if we look back at this algorithm, so we mentioned in the first step we want to have a warm start, so that the warm start can lead us to a good mean prediction. But actually, this is just because we believe in this setup, it can make us a bit easier in the late step because it can give us a properly good mean estimate. But I also agree that sometimes it may mislead. It may give us some not that good part. But here in the step 2 and step 3, as I mentioned before, we can iterate between each other. So in this case, as you mentioned, if we have a really bad initialization, meaning we have a mean neural network, it just doesn't change. I also had that experiment. So which means that in that case, we have to iterate between step 2 and step 3. So we have to go here back and forth for several iterations. Then it will stabilize and give us good predictions overall. So
if I may add, your question is very good, but you have to think about one thing. If you do everything at once, like Yaga said before, what happens is that you have to optimize for the mean and the aleatoric uncertainty at the same time. And what we found out is that if you calculate the Hessian of the network, the outputs of the network, with respect to the mean and the aleatoric uncertainty with a variance, you actually have a saddle landscape at the last layer of the network. And so what happens is that when you optimize for this network for more than one metric at once, you can get your gradients to be 0 and have a mediocre prediction for both things. Do you see what I mean? So in essence, we didn't find cases where it was worst to do it cooperatively like we propose. The trade-off is that it may take 1 or 2 iterations to get there. And so far we didn't need more. But Yaga has run cases where he has the tail ends and the beginning and the middle of the data set without data. And so where you have a prediction of the mean that is not perfect in those regions, exactly what you said, but the predictions are still always better than predicting everything at once. You see what I mean? Because the optimization problem itself is much trickier to do if you're doing deterministically. And the sampling, if you do HMC or any other kind of inference, is also more difficult for the same reasons, right? If you have a saddle landscape, it's also harder to sample for that than if you don't have it. Does this answer your question? Do you see what I mean?
Right. I understand, because you cannot optimize the mean and the standard deviation at the same time. So you need to alternately change the values. Yeah.
Exactly, but you get a well-behaved landscape, especially for the variance if you use the gamma likelihood that we propose. And so there are no numerical issues anymore. And of course, the trade-off is that you need to wait to get the first estimate so that you can update the second one and vice versa. But in 18 data sets, we showed that for most of them, it converges with 1 iteration. So just doing it once. And I think it was 2 or 3, I don't remember, Yaga, you should tell me. But in a couple of cases where it didn't, in the second iteration, it converged. So it's a very fast convergence. And we have an analytical demonstration of why that is the case.
Okay, thank you very much. Another question about the framework is that, have you already considered incorporating the physics-based laws into this framework? It is possible?
Yeah, thanks for your question. For now, we haven't considered to have physical information, but I think it should be logical to do in the next step.
Okay, thank you. Thank you very much.
Do we have any other questions?
So
yeah, I would have one.
Go ahead.
Okay.
All right. Hi, this is Joshua. I'm a postdoc with the Crunch group. I'm currently okay. Okay, my camera is unable to access camera. I'm sorry for that. Yeah, sorry. Camera doesn't work. So yeah, I'm postdoc with the Crunch group. I had a question. You might have addressed this right before, but I got disconnected just a minute ago. Is this iteration between step 2 and 3, is this sort of an expectation maximization scheme?
Sorry, and I cannot hear you very well. Can you repeat the question?
Yaga, the question was if the step 2 and step 3 is equivalent to expectation maximization scheme.
Yes.
Yeah, you can. Yes. In this case, you can imagine this is the setup.
Okay, thank you.
Really,
and
yeah.
And then I have another. It's more of a comment rather than a question. Is so from the interpretation what you do. So you say you disentangle the aleatoric and the epistemic uncertainty. From my understanding, I think what you actually do is you approximate the combined uncertainty with a vanishing entanglement, because even in linear models or generalized linear models, if you will, you always have interaction terms, or as you call it, entanglement terms. And even if your prior factorizes, and even if your covariance is diagonal, even then you have these mixing terms. So I think you don't actually disentangle the uncertainty, but you approximate the disentanglement to vanish.
Yes, I think you're right. We in this case, because from our perspective, this kind of separating is very important, and in this case, we are trying to getting close to this disentanglement, we call it. But of course, we cannot say it fully disentangled, because from the linear models, as you said, there's always this entangled terms here.
Exactly.
Yeah, I think that's a really interesting comment, Sasha. But the point is that what we do see, and we prove analytically as well, is that it keeps disentangling as you move forward. Do you see what I mean? So when you gain uncertainty on one of them, the other one compensates by going lower.
So you mean you're saying you're shifting, you're absorbing the entanglement term in one or the other, in a sense.
Right. That's why I think you framed it in a smart way. I think you are right, but indeed it is doing disentanglement in that sense. So as long as that's clear, yes, it's doing exactly what you said.
All right. Okay. Yeah, that clears things up. Thank you very much. Great talk. Thank you.
Thanks.
I have a question, Yaga. You mentioned that this framework is scalable, but we know that Bayesian neural networks are not scalable because you assign one stochastic dimension to every neuron. So no matter how you do it, even if you split, of course, you make it computationally more friendly, but you still have the lack of scalability because it's a BNN. That's what hinders BNN for a long time. I don't know if you solved that problem.
Yes. Actually, this is a really good point. So we see it is scalable because that comes from here. Because at the third step, we can choose our inference method. So for notice, we also find that actually the ensemble, though it's not strictly a Bayesian inference method.
We use ensembles. We have a paper, 120 pages. I don't know if you saw it in CISC or JCP, I think. So we use all these methods. We have about 10 methods. And ensemble methods are not very good. The only good method here would be HMC.
Yeah, I agree.
Mean field variational inference. We use it actually to get an estimate of a prior, not for posterior. It's not good. Laplace is not good either. Dropout, you use dropout, but dropout depends so much on the rate, so you have to be careful to do it carefully.
Yes.
The dropout rate. So I mean, no matter what, you have to go to HMC, unless you do things like recently, the first guy who asked you questions, Jiwei Gao, wrote a paper where he could beat HMC in terms of accuracy and speed, but he has to use subspaces, active subspaces for sampling and so on. So that's the thing. I mean, we work on this on Bayesian neural networks and pins, and we switch to functional priors because you're in the latent space. So instead of thousands of dimensions, you are now in tens of dimensions. So that's manageable, for example. So if you're in a latent space, let's say using GANs or diffusion models and so on. So it is not scalable to real systems. That's why you said yourself that you cut these small stumps because you couldn't do the computation. So then you cannot call it scalable. But I have a question here also on the epistemic uncertainty. What is your so this is like interpretation for you to, and because that defines how strong is the coupling between 2 and 3, step 2 and 3. What is the what do you think is epistemic uncertainty? When you talk about epistemic uncertainty, that includes for you what? What are the sources of that epistemic uncertainty. For aleatoric uncertainty is the data noise, like you said, that's fine. But for this case, when you deal with neural networks, what are the sources of epistemic uncertainty? Can you elaborate?
Yeah. So here, actually, as I mentioned at the very beginning here, for our cases, we only consider the epistemic uncertainty for the mean predictions. So it comes from the neural weights. So in this case, I know that there are many interpretations of the epistemic uncertainty, but here we only consider for a given architecture, and we think about the epistemic uncertainties that architecture, the uncertainty from that architecture. But of course, we can extend to consider different architectures that will be a bit more thorough, but of course it will also bring us to more computational sources.
Yeah, that's right.
So yeah, in essence, George, the mean variation, right? So it's hugging where is the expected value of your prediction, and that's the only epistemic uncertainty that is being considered here, right? So you change the weights, and you have multiple models, right? An infinite number of models theoretically that are trying to fit the mean, and all the variation that you get is about that expected value prediction.
Yeah, just for your information, Jag, I have in the paper that I mentioned, a very long paper where the title is Uncertainty, Quantification, Scientific Machine Learning. We have a pie chart that we have all the sources of uncertainty right from the figure 1. So you can take a look at that. So the model uncertainty is actually different because model could be a physical model, for example. For our problems, we're doing physics and have governing laws and so on. So and we have dealt with that. That's totally a different animal, but that's actually the big beast. It's not the epistemic uncertainty, and it's not the aleatoric. It's the biggest uncertainty is the model uncertainty, especially that you work with plasticity and all this material. So that's kind of separate. You have to don't lump it together with epistemic uncertainty. That's a different one. But there's like 3-4 sources of uncertainty, of epistemic uncertainty. That's why I asked that. Because if you take that into consideration, then your network has to scale up. So then that becomes more expensive, as you said, and so on. So it's compounds the complexity. Yeah.
But George, to your point of the scalability, I think one of the things that I feel it's advantageous for this particular method is that no matter what way you decide to do inference, whether you do it in a latent space, subspaces, and you make it substantially more scalable, you can still use this. So we used it for different architectures and all of this, and it just improves. So I think the main point is not so much about what is your favorite inference strategy, but more about you can make the problem a lot simpler by making it cooperative in this way.
Right. But the complexity of the problem, Miguel, comes in also in this approach because you will make the coupling between step 2 and step 3 tighter. Because if those in our paper, for example, we say, okay, you can actually compute the epistemic uncertainty, and then you simply add sigma A square, or sigma A is the aleatoric uncertainty. So that's your total uncertainty, if you like. But that's an assumption which is not valid if you have many sources of uncertainty. So the physical problem would induce a coupling, which I think will result in step 2 and step 3 need to be iterated more.
I understand what you're saying. Yeah, indeed.
2 and 3 iterations.
Yeah, if you include more uncertainties, then this entanglement becomes even more interesting because now there's more than yeah, for sure. But that's very interesting. But the scalability of BNNs is just a beast, right? It's always a difficult thing to do. I think what we meant is for us, George, where we were using Gaussian processes and so on before, the scalability that we are able to achieve now is much bigger for the mechanics problems that we're handling. But if you have millions of variables, of course, then it's not scalable enough.
No, but even for his problems, he didn't do big RVs because the whole RVs because he couldn't compute it. He said that it was too expensive.
Right. To get the data itself, right? Not the inference strategy, just to be clear.
I see.
You see, so the RVEs, each RVE can take several hours in a supercomputer to get the data, right? But not so much to compute itself.
Okay.
For the regression part, yeah, that's true.
All right. Thank you very much.
Yeah.
Thank you. Do we have any other questions, comments for the speaker? Okay. Thank you so much, Jiashang, for your great talk. And I think it's time to close the session. Thank you, everybody, for joining us today. Have a great weekend ahead. Bye.
Thank you. Bye-bye.
Thank you.